Okay, probability in a discrete uniform distribution. So what this means is when you have a distribution and all the probabilities are the same. So the probability of 1 is going to be, say for example, rolling a die, it's going to be 1/6. Rolling a 1 and rolling a 2, it's going to be 1/6, and rolling a 3, right? And 4, 5, 6. So all of these probabilities are going to be the same. If you think about it, when we think of uniform, we think all the same. Okay, so the probability of a discrete uniform, we just put 1 over n. N for this case, like rolling a die being that 6. Okay, there's 6 different outcomes, so all the probabilities, each one is going to be 1 over 6. And the expectation for this, what we do for expectation, so there's like a formal equation here, but what we do is we multiply each probability by its outcome. So for example, 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6, and so on all the way to 6 times 1/6. So the expectation is the expected outcome of an event, and we'll get into that. So what you're expected to roll. Okay, it doesn't necessarily have to be one of these numbers, a 1, 2, 3, 4, 5, or 6, right? But it's going to be what you're expected to roll. So, example 2, let's determine the probability distribution of the outcomes when rolling a single die, and we're going to graph it. Okay, so first, x is going to be the random variable. Okay, let x be the random variable. Of the number, random variable of the number rolled with a die. Okay, so again, random variable is like every single outcome rolled with a die. Okay, so I would make a chart. Every single random variable. So what are all of the outcomes? 1, 2, 3, 4, 5, and 6. Okay, I would make a chart. Now, what's the probability of random variable x? Well, to roll a 1 is 1/6. To roll a 2, it's 1/6. 1/6, 1/6, all the way down. Okay, because we know that it is uniform. Now, if we want to solve for, so this is the probability distribution, okay? So I'm just going to kind of take this one step farther, only because we have it already here. If we want to solve for the expectation, so what we do is the expectation of x is just x, I call it squiggly xpx. So the sum of all of the x's times the p at x. So let's do 1 times 1/6 is 1/6. 2 times 1/6 is 2/6. And my advice is not to reduce these because it's just going to be easy. And you're going to see at the end, 3 times 1/6 is 3/6. 4 times 1/6 is 4/6. 5 times 1/6 is 5/6. And 6 times 1/6 is 6 over 6. Now, what we want to do is we want to total these. The reason I said not to simplify these is because now all of these numbers are over 6, so they all have a common denominator. So we can simply go 6 plus 5 plus 4, which is 15, plus 3 plus 2 plus 1, 15, 16, 17, 18, 19, 20, 21. So the answer is 21 over 6. And if you calculate this, it's going to be 3.5. So the expected value is 3.5. Now let's graph it. Okay, so we have a graph now, and what we want to do is along the bottom, we can put the random variable x. And up the side, we want to do p at x, so the probability of x. Okay, always the probability is going to cap at 1. So let's actually do 1/6. Okay, and that's because the probability of any event occurring is equal to or between the numbers 0 and 1. So let's put this as a 6, and then I'll put a squiggly here just so that we know that it's not like if we go up this many boxes, it's not going to be 1/6, 2/6, because that would clearly only be up to like 3/6 here. Okay, so we're going to do the probability of 1/6. Let's do the random variable 1, 2. I'm going to do a bar graph. So S1, random variable 2 is going to be the exact same height. The random variable 3 is going to be the exact same height. Random variable 4. Random variable 5. And the random variable 6 are going to be the exact same height. And that's probability distribution as a graph.